Welcome back, Physics 30. Today's lesson is mass spectrometer. It's basically the combination of Unit B and Unit D together. Unit C does not mention much in here because we are not talking about gamma radiation. So first thing first, mass spectrometer is basically a laboratory equipment for quantitative analysis. So quantitative analysis means you are basically try to use whatever sample amount, and by undergoing proton, electron, how much of them and how much is an emphasis. And by going through that, you will find out what kind of isotope ion are you dealing with. Basically, we use similar concept as Thomson's device of cathode ray tube and Q over M charge to mass ratio to determine the nature of different isotope that is involved inside of an element. And you have multiple sections in here, but I like to divide this into first, ion generation and acceleration chamber. Number 2, velocity selection chamber. And number 3, ion separation chamber. And each of those sections will be explained differently. Let's go with first chamber first. First thing first, there is a powerful energy source that is included in this chamber. You have some kind of sample that goes into this area, and by undergoing some kind of high energy that is exposed to this environment, and that can be flame for some, that can be plasma. Plasma is a quite well-known additional source of energy that will be useful because I believe from my long time memory in university, argon gas is used as a source of it, and it's one of those extreme heated physical state. It's kind of a highly energized flame, if you will. It's extreme, but in any case, it instantly excites the sample, and with the electron beam, it's gonna be ionized. So that's why the first chamber, the very first step inside of the first chamber is ionizing sample. And when it comes to ionization, generally in Physics 30 you have two situations, but it can be more too. Singly ionized or doubly ionized. When it comes to single ionized situation, think about, like, for example, Na+, K+, so sodium, potassium, those are the situation. Not all the time, it can be metal too. Like copper and 1 positive, something like that. Double ionized can be like 2 positive, like calcium, magnesium, those kind of situation. And of course, it can be metal too, like I said, copper 2 positive, something like that. And singly ionized, 1 positive means you lose 1 electron. Doubly ionized, which means 2 positive, and thus 2 electrons are lost during the process. How can we accelerate ions in here? We basically use potential energy. So here's mathematical depiction of how battery play a huge role. External battery, because external battery means I have potential energy, and that potential difference from one area to another will converting into kinetic energy. And now, assuming that initial velocity was 0.0 meter per second, something like that, which was rest initially, then we can set that Q delta V is equal to 1 over 2 mv squared, and this V will be my final speed. So if I isolate for V's perspective, 2Q delta V over M, and then put square root around that. So you can basically detect speed when the ion exit to the chamber number 2. You can do that calculation. Please remember this value because this value will play a huge role in the second chamber. And second chamber is basically known as velocity selection chamber. This area, it's very similar to cathode ray tube, and it's Thomson. That's what I'm gonna put. The reason being is, like the word suggests, we are specifically control a speed of it. Only this type of speed will go undeflected, and that's a key word in here, and go straight. If the speed differs, then some of them will be attracted to above or down. So when it comes to this situation, if you look at it, imagine there is a positively charged ion that goes through this chamber. Then know the fact that in order to be undeflected, you should experience FB magnetic force, or FM, sorry, and then FE electric force. So you need to have a balance of the force. So velocity selection chamber basically have external electric field and external magnetic field, and only a correct one type of speed will be chosen and travel undeflected. And the way that you can find it mathematically is Fm, just a quantity, should be equal to Fe, and will be QVB, and Fe is QE. So you may notice that charge will be cancelled. This is one of the main reasons why mass spectrometer is really useful, because in the process of ion generation chamber, you don't always make single electron or double electron. It can be triple or quadruple too, but only certain ion can go through. But if you control the V setting, so electric field and magnetic field, and eventually if you get this conclusion, you don't technically have to deal with whatever the unknown charge of isotope. You don't need to, or ion, sorry, isotope was a bad word, ion of it, because Q will be cancelled out mathematically. Now third, ion separation. This part is basically unit B, your left hand rule, right hand rule number 3. Of course, right hand will be the one that will be used a lot because we use positively charged ion, and it's gonna turn into this way. So in order to make that happen, forefinger should be pointed outside of the picture, so it must be like this, outside of the page. And by having that set up, you may notice that the detector screen is over here. Only the certain chosen one that goes in the middle or something like that will be the one that detected, or if it's further, that's less charge, more charge, something like that. So it is left hand rule, right hand rule number 3. It does involve centripetal motion, so circular motion. One thing that you need to understand is this is not a parabolic motion. This is not throwing baseball horizontal way. It is circular motion done by centripetal force. So ion separation chamber start with Fc, that is equal to Fm. Oops, vice versa. I switched them apart. I'm just gonna switch them apart. Really doesn't matter anyway. MV square R. Field will be gone. And if I isolate for charge to mass ratio, Q over M, that is equal to V and R B's at the bottom. So if you find out a specific speed that exits the first chamber, and imagine that speed is what the machine try to detect, then it's undeflected, and using that speed, we can actually do the analysis to find out charge to mass ratio. And in this way, not only experiment basically can figure out certain mass is quantity, so that's why I put quantitative analysis in chemistry actually use this a lot. And they can also determine the percentage of each of the isotopes, so how much it presents, something like that. And basically, if you want to go with the bio situation a little bit, paleontologists who learn about dinosaur fossil, those kind of sample, carbon dating, we can use the mass spectrometer as a tool for the analysis, because you can basically find out, oh, there's almost this much a percentage, and you can use half-life, the one lesson that we know before this, and combine those together. Let's do one classic example. Gonna do hopefully the tough one at the very back, number 7, and after that the lesson will be done. So let's go through this. Triply ionized vanadium 51, which has 50.944 U. Isotopes are accelerated from rest through a potential difference V. They then enter perpendicular 750 microtesla magnetic field and go into circular motion with the diameter of 40 centimeter. Find the total potential difference V. So let's figure out what clues that is given first. Q is given, it's positive 3e, so that means 3 and 1 our fundamental charge, and if you punch those number in, you will have 4.80 10 to the power of negative 19 C. So that we know. We also know mass, but of course mass is 50.944 U. So if you multiply by a 1.67 10 to the power of negative, conversion, you will figure out 8.46 10 to the power of negative 26 kilogram. So 1.67 10 to the power of negative 27 times by this should give you that. It's a good idea to go to a unit that we generally use, which is known as basic unit. Magnetic field is also given. 0.750 is good enough for the Tesla. Don't need to put scientific notation for everything. Same thing for R, which is 0.400 meter. Actually, divided by 2. Almost forgot. It's diameter, so 0.200 meter. So how can we use these clues? First thing first, we need to go with third chamber first. Because we're talking about the relationship between radius, which is Fc, that is equal to Fm, magnetic force. Why this is important? Because mv squared over r combining with qvb, we can isolate in the perspective of speed, like this. And that speed, ladies and gentlemen, can be used to figure out our first chamber, which is the one that talk about potential energy converting into kinetic energy. And we can just combine these two together. It's your choice of punching the number in and keep that number. Let's just use this entire thing, modified formula, into our final step. Now, potential energy is Q delta V, and that's what we try to find. that is equal to 1 over 2 mv squared. And that is basically what we try to substitute. So if I continue isolate stuff, we know that delta V, maybe I'll just put that over here, is equal to 1 over 2 mv squared divided by q. That's what happened. And if we simplify before, 2q mv squared is what we have. And now if I substitute everything, m qbr over m squared 2q is what we need to do. And we can actually simplify a little bit, because m times q squared b squared r squared over m squared over 2q. That means q and single q cancel, and so as m. So 2m is located at the bottom, and you have qb squared r squared is on the top. Now I can punch everything in. So making your life a little bit easier. Then delta V turned out to be 6.39 10 to the power 4 volt, or 63.9 kilovolt. That is today's lesson.